Imagine a surge of electrical charge hitting a conductive system. This specific system consists of an inner shell A and an outer shell B, separated by a distinct physical gap. A voltmeter placed across this gap records a steady potential difference, a direct measure of the electrical work required to move a charge between these two boundaries. Now, suppose we flood the outer shell with a massive new amount of charge. Intuition suggests that such a drastic change to the boundary must alter the reading on the meter. If the exterior environment changes this significantly, what actually happens to the internal gradient? The outcome of this scenario is often the opposite of what a first glance suggests. In concentric systems, the potential difference across the interior gap is mathematically independent of the outer shell's charge. It is anchored exclusively to the charge on the inner shell. Reconciling this with the physical setup requires looking past the surface and rebuilding our understanding of spherical potentials from first principles. The macroscopic view obscures the underlying behavior. Only by deriving the state of each shell can we see how these values actually interact. We start by isolating variables, focusing on a single charged spherical shell with its own radius and total charge. Outside this shell, the potential behaves exactly like a point charge, decreasing inversely with distance. Inside, the rules change. With no electric field within a hollow conductor, the potential remains uniform at every single point throughout the interior. This interior potential isn't zero. It is locked to the constant value found right at the surface. Effectively, a charged shell creates a region of constant electrical potential across its entire hollow volume. Now we reintroduce the second shell, an inner shell A with radius R1 and charge Q1, nested inside an outer shell B with radius R2 and charge Q2. Using the principle of superposition, we determine absolute potential by summing the individual potentials. We define the absolute potential on the surface of the inner shell as VA. This specific point is heavily influenced by its own surface charge and its position relative to the outer boundary. This gets us the first expression. VA includes the potential generated by its own charge, Q1, at its radius R1. But because this point is also inside shell B, it inherits shell B's constant internal potential, adding a second term. Next, we calculate the absolute potential at the outer boundary, VB. At this radius, we are outside shell A, using the distance-based formula, and directly on the surface of shell B. In both of these, absolute potential shell plays a significant role in the final value. To find the potential difference between the shells, we subtract VB from VA. Stacking the two equations allows us to see how the terms cancel. Because the internal potential from shell B is identical at both points, that term appears in both equations. When we subtract, it disappears entirely. The algebra removes the outer shell's charge from the result. The difference is determined only by the inner charge and the geometry of the shells. We can apply this to a standard test scenario. Here, the initial potential difference is 5 volts. When we add more charge to the outer shell, the potential difference remains exactly the same. It's similar to a canal lock. Adding charge to the outer shell raises the absolute potential of everything inside it equally. Because both shells rise by the same amount, the gap between them is unchanged. For nested shells, if the inner charge doesn't change, the potential difference won't either. This algebraic cancellation reflects a deeper law of electrostatics. The electric field in the gap is produced only by the enclosed charge, shell A. The outer shell cannot produce an electric field inside its own hollow interior. Since potential difference is the integral of the electric field over that distance, the outer shell has no mechanism to change the voltage. While an outer boundary changes absolute potential, it cannot shift the internal gradient. The difference is always